off, which is the end of chapter 7, which includes the change where now L is growing at rate n. So one of the key lessons here is that when you start including the assumption that L is now growing, economic growth then will depend on the capital accumulation equation or the change in K equation. And the change in K equation, if I can just go straight up, it's this one. Okay. And what this is saying is that a higher N will lead to a smaller K star, steady state capital per worker. And the reason is that because the denominator, which is L, remember small k is big K over big L, the denominator is growing at rate N, and therefore, since it's growing at rate N, it's harder to equip each worker with capital. Okay, because the denominator is growing, more and more people are coming in. And so it's harder to produce more and more capital for them. So as the change in K falls, it will fall to a level that is equal to delta plus N here, which means because of diminishing returns to capital, you will have a smaller K, right? So a smaller K will equate this equation here equal to 0. So there's more K per L. L is growing, so it's harder to have a higher steady state capital per worker. So that's one of the big conclusions or predictions from the Solo model, that a higher growth rate in your population will mean a lower capital per worker in the long run, which means in the long run, your Y star or your output per worker will also be smaller. So that's one reason why N can affect output, right? Because that means that a higher N, more L, more labor, it will be harder to produce the capital to make sure that everyone gets a certain K over L. And that's why the economy will end up with a smaller K over L. Okay. So that's one way of viewing the effect of capital. The effect of the growth rate in labor, which is again how it will affect the steady state K. Couple of other interpretations, alternative perspectives on population growth. There are two. So first is the Malthusian model, which basically states that a higher N means that population growth will in general be much, much faster than capital accumulation, according to his model. And in particular, ultimately it will lead to poverty, right? So essentially that capital accumulation is not powerful enough to be able to solve the problem of growth, and then ultimately growth will become 0. So in a sense, it's quite similar to the Solo model because it'll have it has a similar flavor, right? More labor means that you need to produce more and more capital per worker, and that will become difficult, assuming that there's no change in the efficiency through which we use labor. Therefore, in the steady state, it will be the same. And the Solo model, as well as the Malthusian model, output per worker, the growth of output per worker will eventually be 0, right? The Malthusian model just has an additional sort of assumption that it's not just our steady state output per worker is lower. Humanity will in fact be mired in poverty, because it is his expectation, his theory, that N will not just grow at rate N, it'll grow faster and even faster than capital accumulation and attempts to accumulate or increase K. So therefore, it will in fact lower output per worker in the end, even more than in the Solo one. So one of the key limitations of this Malthus's model is that there are other effects of a larger population, okay, and that more people will result in more ideas and more technology, better and more efficient technology, and that in a sense will offset the stark predictions of both the Solo model and Malthus, basically, wherein Malthus would have said that poverty is inevitable if people's ingenuity or ability to create new ideas and to more efficiently use capital and labor, if that's true, then you can basically escape the poverty trap that Malthus has envisioned due to the increase in the population. Not stated here, okay, which well, it's sort of implicitly stated here in the last one, and that ultimately the size of population growth, which assumed in Malthus is very, very high and only is growing, the reality, in fact, that's in the news recently, the growth rate of population of the world is in fact getting smaller. And some places around the world, the size of the population is in fact shrinking. And speaking of the Philippines, we're basically at the replacement level at this point. So basically, there's a period where our N or our growth rate in population was very high, but now it also has fallen, and that the desire to procreate, to have more children, will tend to fall as economies develop, for many reasons, right? One of them would be you'd want to invest in your children, and therefore you have fewer children. And typically, the higher the GDP is, the larger your opportunity cost of time is for investing in children. That's one reason of many, which will point uh, to a force that will lower your growth rate in labor. Right? So yun yung dalawang pagkukulang, right? The failure to think about the growth of efficiency here, mankind's ingenuity to come up with new ideas, and second, the population growth will basically not grow as fast as it had before. And over time, in fact, there's a tendency for the population growth rate to fall as economies develop. Another alternative idea, okay, that's not explicitly included yet in the Solo model, is that a larger population will tend to create new opportunities for people to work together. New ideas can pop up, and that ultimately is the source of long-run economic growth. You can read some of the details here, but Kremer basically says that a higher population ultimately, at least globally, will be associated with larger long-run economic growth, which is the growth in efficiency of labor and capital. Okay. So that ends chapter 7, and which allows us now to go to chapter 8. Okay. And chapter 8 is the final form, if you will, of the Solo model. And the key difference here is that our production function, okay, is now a function of capital and efficient labor, L times E now, right? Where labor is not just the size of the labor hours here, which is the number of people times the number of times we spent working. It's also going to be the product of that times the efficiency of labor, how efficient or how productive labor is. So E is a new variable that we are going to include, okay? And you can think of it as the efficiency of labor. L times E is now going to be the effective number of workers. So you can imagine E, for example, if each worker can produce twice as much as it did before, so E grows to 2 from 1, then even if your L does not grow, then L times E has grown. So the effective number of workers has in fact grown. All right. So, and this is again another example of labor augmenting technological progress, because it's the efficiency of labor that's growing, and it's connected intimately to how efficient labor is. We are going to assume that E, or the effectivity of labor is growing at a given percent at rate G. Okay. So that's the last thing that's going to change. So before we go to the actual equation, let's write some things down first. So I'm just gonna insert a text box here. And I have a K, okay? And my second text box will have an L. And my final text box will have, right? And of course, they're all associated with Y, right? So Y is going to be a function of, uh, what it's going to be Y over EL now. And if this is going to be equal to your Y or your small y. So instead of Y over L, now it's going to be Y over EL or effective labor. And that small y is going to be a function of K or small k. Wherein your small k is now going to be this one, this k here. Just going to make this as big as possible. Wherein this k here is here. And then I'm just going to draw a line there. And then I'm going to grab this one. Your L is below, and then your E. Just gonna add an E here. E times L, right? Okay. And this has to be small k, of course. There you go. All right, so now your small k is going to be this ratio between k and E times L. So that has changed. That's the thing that has changed now in the full set specification of the solo model. So recall that L is growing at rate N, and now E is growing at rate G. All right, I'm just gonna erase this to make sure growing at rate G. So that means your denominator is growing at rate N plus G. You can add that here. E star L is growing at rate N plus G. Okay. The other thing we remember, of course, is that K or big K is becoming smaller. It's shrinking at rate delta depreciation. Okay. So what's happening to small k? Small k is going down because k is shrinking, right? And it's also going down because E and L are both growing. So remember, if the denominator becomes bigger, the whole thing becomes smaller. So these three different things will come together to basically limit the size of K star. Next. So now let's re-examine the equations for this general case where you have the growth in labor and the growth in technology. And look at the delta K equation. So your delta K equation is still S times F of K. So again, this is the investment equation. Okay. So this is how K is growing over time. This is your you're setting aside S% of your output per worker, per effective worker. You're setting that aside to increase your capital per effective worker. And then you have to overcome these three things that we've said: delta, which makes your K smaller, N plus G, which makes your K smaller also because it increases your E times L. So this is your delta K. Remember, if this is also governing how fast you're growing. So if delta K is growing, then delta Y is also growing, right? And at the steady state, your delta K is no longer growing. And at the steady state, your delta Y is no longer growing. The equation, the graph, it's still very much the same, right? The blue line still starting from the origin, but now its slope is delta plus N plus G. Okay? So basically, it's a steeper line from before. The more elements you add here, the steeper that line will become. The red line is still f of k, the intersection of which will be k star, which is the steady state, wherein the steady state is defined as the k, which makes this delta k equal to 0. Right? So your k is no longer growing, and therefore your y, small y, is also no longer growing at the steady state. Let's go first to the golden rule. So the golden rule idea is still very much the same. So you're maximizing C star, right? And C star is just output at K star minus what's called the break-even investment. So this is the level of investment where your delta K is equal to 0, right? If your investment is equal to this, that means that's just that's exactly the amount of investment you need for your K to stop growing or stop falling, where your delta K is equal to 0. That's why it's called break-even investment. So this is the maximal consumption. You take the first order condition, or you take the derivative. The derivative of this is just your MPK, and the derivative of the second bit here is just all of the constants, delta plus N plus G. And this formula here will give you the size of your K goal. Now, again, I remind people, your steady state and your K goal is not necessarily the same. Your K star, your steady state K, can be higher or lower than this, right? The thing that will make it equal to each other will be the S, or how much you have decided to save, which is part of which is at least settable by the government. Yeah. Okay, this table 8-1 is super important. This kind of summarizes everything that we know about the Solo model. So capital per effective worker, which is small k, which is big K over E times L. At the steady state, your delta K is 0, and therefore the growth rate of your K is 0. That's what delta K means. Your K is no longer changing. Delta K is equal to 0. That's when the K is no longer changing, because that's the steady state, or delta K is equal to 0, right? So the K that makes delta K is equal to 0, that's going to be called your steady state. And at the steady state, this one is not growing anymore. It's not growing, not because all of the parts are not growing, but because the numerator and the denominator are growing at the same rate, right? So it's like this is going up by N plus G percent, and the denominator is growing by N plus G. And therefore, if the numerator and the denominator are growing at the same rate, that's therefore the ratio itself is not changing. Next is output per effective worker, big Y over EL. Now, big Y over EL is a function of a small k, which is the same k as this one. Now, if the k is not changing, then your Y is also not changing. So therefore, in the steady state, your Y over EL is not growing also, right? Because small k is not growing. But here's the interesting part. The output per worker, which is just Y over L, not Y over EL, but Y over L. That is growing at rate Y times E. Now, small y, is growing at rate 0, like we said, but then E is always growing at rate G. Therefore, at the steady state, your output per worker continues to grow at a constant rate, which is G. Okay. Next is total output. which is your big Y. Your big Y is just the growth of small y times E times L. Okay, because the small y is just by definition big Y over E times L, right? So the big Y will grow at the rate n plus g. So this makes total sense, right? Because your big Y is basically a function of big K and E times L. Okay. If that's the case, if your big Y is a function of big K and E times L, then because you know that K here is growing at rate n plus g, and your E times L is growing also at rate n plus g, therefore by constant returns to scale, if your K and your EL are growing at the same rate, your big Y is also growing at that same rate. And that rate happens to be n plus g. So this quote unquote solves the problem of steady state growth. In the long run, we will all grow at the steady state growth rate G per if we're talking about output per worker. And assuming we all have the same K star, we'll talk about this in a moment, we are all going to converge to that same growth rate. However, as long as we're not yet at our K star, our growth rates will be different. So the further away we are from the steady state, the higher the delta K will be, and the faster the growth rate is. So essentially, we're growing fast, but over time, our growth rate is becoming smaller over time, and as we're approaching this tree. All right. So next, let's talk about some growth empirics. Okay. So first, let's talk about balanced growth. So a feature of the solo model here is a property called balanced growth. Okay. So what is that balanced growth idea? The balanced growth is first, consider Y over L, which we had just talked about, and then K over L. So according to the model in the table above, these grow at rate G. Okay. So output per worker and capital per worker, they both grow at rate G, right? Which is the rate of technological progress. Um, so data from different countries will show that there seems to be a constant long run growth rate for different countries. And that could basically be an estimate of how fast technology is growing at rate G. So empirically, people have used this sort of long run growth in Y over L to get at how fast the technological growth or TFPG is growing. So now we had called it the efficiency of labor, but another way of viewing this in general would be total factor productivity per tree, right? Okay. So anyway, what else? If you notice, if you take the ratio of Y over L and K over L, the L's will go away. And what you'll have, so let's write that down. So let's do, if Y over L grows at rate G, and then K over L also grows at rate G, then what you'll find is that the ratio of them, which is Y over L, that's big L, and then divided by K over L, divided by K, which should be equal to Y over K. Therefore, that is constant. So the output per capita, or you can imagine the reverse, K over Y, that is also constant, okay, in the long run. And that should also be evident in the data. Okay. So a couple of interesting implications for this. These facts here will help you understand what's happening to MPK and MPL, right? So MPL, marginal product of labor at the steady state, is also growing at rate G. Okay. The reason is that MPL is a function of K over L. Okay. So you can calculate that. MP MPL is going to be a function of K over L. And in this case, since it's growing at rate K over L, MPL is growing at rate G. You can solve for that. The other interesting part is, well, actually it's not K over L, it's Y over L. So MPL equals, if you recall, alpha, which is the share of labor, times Y over L, right? Which is against a function of K over L. Since Y over L is growing at rate G, then that means your marginal product of labor is also growing at rate G, which tells you that the real wage rate is going to grow at rate G in the long run. Now, MPK is the share of capital, which is 1 minus alpha, usually. And it's going to be Y over K, right? And since Y over K is constant, okay, because of this fact here, then MPK is also constant. Oops. Here. So these are some facts about how wages, real wages and real rental rates are also changing based again on these results here from the solo model long run or steady state. So that's this part where you have a prediction on the factor prices. And that's this part here, problem 3 at the end of the chapter. Next concept is called convergence. So what is convergence? If the K star for all of the countries are the same, then if the only difference between countries, poor countries and rich countries, is that the poor countries have less capital per worker than the rich countries, then that means both the poor countries will have a faster growth rate than the rich countries. Okay, that's empirically true. And then there's a form of catch up. The poor countries are growing faster and therefore they're catching up. And then they're going to converge to the same output per worker as the rich countries. So this prediction has proven to be correct generally as long as you assume that the different countries will have a similar K star or long run capital per worker. Steady states, right? If two countries though have different steady states, then you don't necessarily expect convergence to output. Okay? Instead, each economy will approach its own steady state. So there's evidence of this empirically. It's if you were to look at the literature, it's going to be called what's called conditional convergence, which is if you're similar, otherwise similar, then the model will predict a conditional convergence. The poorer you are relative to your rivals or your other people in the same neighborhood or same geographic otherwise similar countries that then the poorer country, the one with the smaller capital stock, will tend to grow faster than the richer country. So that's called conditional convergence. So this is what in the textbook this complex picture emerges. Okay, so you'll have a conditional convergence. They appear to be converging to their own steady states. So that's conditional. Next concept is factor accumulation versus production efficiency. So as a matter of accounting, international differences in income per person, or Y over L, can be either coming from differences in the factors of production, okay, and of which, by the way, we have been focused on. The solo growth model is all about accumulating capital. The forces that push you to accumulate capital. So, and convergence is also about differences in your factors of production. That poorer countries or countries with less capital per labor they're the ones who will grow faster, right? Than rich countries. But there's also a second factor here, which is differences in the efficiency with which economies use their factors of production. Okay. So this is basically the same E, or labor efficiency. You can also recast it. So from now on, instead of labor efficiency, we will now call it total factor productivity, because in growth accounting, we are basically accounting for all of these differences and the growth and factors of production, and we are sort of netting that out from the growth of Y, and that will tell you what the efficiency of the factors are, right? Because whatever growth is left after that is accounted for by the growth in factors, then the rest of it, the residual, is basically going to be called, it is going to be due to differences in the efficiency for which economies use their factors of production. Okay. So from this point, it will be better if we move to the end of the chapter, and discuss growth accounting. So this is in fact what this whole section is, right? Factor accumulation versus production efficiency. And in the textbook, it's the end of this chapter, chapter 8, will have this growth accounting section. Okay. So now let's talk about it. So it'll be much clearer what we are talking about when it comes to factor accumulation versus efficiency as to help you account for the sources of growth. Right? So first, you have your production function here, which is a function of K and L. Then you'll find that if you change capital, it will change Y based on MPK times the change in capital. So the interpretation here is purely super easy, right? If your K goes up by 1 unit or 10 units here, each unit will contribute to a given number of increase in output. That's basically what MPK means. So you multiply your change in K to MPK, and that will give you the change in Y. Same thing goes for increases in labor. So if you increase L, that will increase your Y by MPL. And therefore, the share of the change in Y, the part of the change in Y that's attributable to labor, is basically the delta L times MPL. So now these two things, this MPK times change in K, this MPL times change in L, these are your factor accumulation components of your change in GDP. And we can write that out here, right? That holding the technology constant, any change in GDP is attributable to either the change in K or the change in L. Here. Okay. Now, generally speaking, once we account for technological progress, you will get the following term here, right? So your growth rate and output will be two things, right? The factor accumulation component here, wherein the factor accumulation component will be accumulating K and accumulating L, both of which will contribute to the increase in GDP. Okay. The alphas here, alpha and 1 minus alpha, these are your marginal products of capital. Okay. These ones are your these play the role basically of the marginal product of capital and labor. Marginal product of capital and labor, right? Yes. So this is the contribution from capital, and then this is the contribution from labor, right? Similar to what we had written here. Oh yeah, this is a better derivation of what I had just mentioned. So here is your contribution to capital. Here is your contribution from labor. And MPK times K over Y, this is the share of the real wage of capital. By the real wage of capital, I mean real rental of capital. The share of that in GDP. And here is the share of the real wage of labor with respect to GDP. And that's going to be either alpha and 1 minus alpha. So in this case, alpha is the share of capital. In the previous slide, PowerPoint, I had mentioned that alpha is the share of labor. So you can do it either way. Right? It's up to you. But alpha is the capital share here, and 1 minus alpha is the labor share. So you can, as long as you've properly identified which share is which, then describe which share is which, then you can use whatever you wish. Next. So here we have those capital accumulation and labor accumulation components. These are your factor accumulation components when taken jointly. Whatever that is left, that's not whatever growth in output that's not explained by capital and labor is going to be explained by the growth of total factor productivity. And it's total factor productivity because it's all of the different factors put together, right? Anything that's not explained by any of the factors will mean that it's due to the growth in total factor productivity. In the data though, this one is generally not measurable direct. And in practice, an economist would use data on a GDP here. It would use data on investment here. It would look at the growth rate in the labor force here. And these alphas here will either be estimates of marginal product of labor and marginal product of capital, or these would be measures of the share of capital and labor respectively in output. So you can use these terms here, alpha and 1 minus alpha, here and calculate the residual or the difference between the growth in GDP and the contributions of capital and labor. What is remaining, what's left over, is going to be due to the growth in total factor productivity. So delta A over A is the change in output that cannot be explained by changes in inputs, right? And it's basically called the total factor productivity, or to honor Robert Solow, it's going to be called the Solow residual. Okay. And then the final part here is that there's a note here that you can actually use this theory to literally account for economic growth. In the United States, for instance, you're able to do this. In any country, actually, you're able to do this. The growth of output here, and then you can calculate the sources of change in GDP from capital, from labor, and these are your factor accumulation elements like K and L. And then what's remaining is going to be coming from total factor productivity. So these are implied values based on the data on GDP growth, data on changes in K, changes in L, and the macroeconomic data on the size of alpha, and 1 minus alpha. Okay, so before I return to chapter 8, I want to briefly talk a little bit about some of the empirical work, because I think it's super interesting and super crucial to get that bigger picture about how well the solo growth model can be used to interpret the data on economic growth in the real world. So the solo model is again focused on these proximate sources of growth, which means changes in capital and changes in labor, right? And changes in PFP, which is the total factor productivity. What are these three things affect on GDP, and how much of GDP can be attributed to these three proximate causes? Okay. So the reason why it's using proximate causes is because there are these other causes of PFP, which are basically these longer run ideas. We'll get to them when we get back to chapter 8. But for now, we're trying to understand how GDP growth is affected by changes in K, L, and PFP. Those are the proximate changes. So the only thing I really wanted to point out here, okay, is that Mankiw gives you essentially the same thing that the textbook gives you, right? This is the growth rate in GDP. These two here will be the contributions of capital and labor, wherein we have data potentially on delta K over K and delta L over L, and these are just the shares in output for capital and labor. And this is the thing we don't know, which is the aggregate production functions technology, or TFT. So that's TFT. And we can compute for TFT here, wherein you're just using X hat instead of Y, right? X hat is just going, well, not X hat. X hat is the TFP itself, whereas G is going to be considered as your Y, right? Your output. It's a change. There's just a change in letters. So G is now Y dot over Y, right? So X hat here, which is just your TFP, is just the difference between these three things, which are measurable, right? So all the right-hand side terms are estimates based on what we get from statistical authorities. So you can continue to read this. And what we wanted to show here, well, let's go for this one first. Can skip a lot of this. Okay. So this is what the growth literature first attempted to estimate, right? MRW will first estimate equation 6 without the human capital term. So basically, it's the model that we have been working on. So ln y, or the log of output per worker, is going to be a function of, look at this, n, g, and delta k. So these are exactly the variables we've been studying so far, whereas n is the growth rate in population, okay, on workers, the worker size, the number of workers. G is the estimate of your total factor productivity. Delta is your depreciation rate. And these things will basically have an implication on the steady state level of Y here, as well as S of K, which is basically your savings rate. So everything in the solo growth model can be taken to the data, and you can basically estimate these coefficients here, which, as you can see, are functions of alpha, right? Whereas alpha is the share of capital in output, uh, which is the coefficient of the Cobb-Douglas production function on capital. So all of these can be estimated using actual data. In fact, this is what MRW, where M stands for Mankiw. So this is one of Mankiw's most important papers here, trying to test the solo growth model using actual data. So at this point, we are going, they do a bunch of things to try to improve on the standard regression for the solo growth model. So I won't tarry with that here. What they have basically done is to uh, add this investment in human capital, right? And that capital is really a larger concept. It's not just machines and buildings and so on. It's also investment in people and people's knowledge. So when you include the share of human capital, the investment in human capital, then the coefficients will start becoming better, closer to what you might expect when it comes to the interpretation of alpha and beta in terms of the share of physical capital and human capital in output, right? So um, when those variables are added, these coefficients will start to agree with the empirical or measured shares of capital and human physical capital and human capital in GDP. So this is something that you might encounter in the next macro series. So I'm going to leave the discussion on refinements on the empirical testing of the solo growth model to that time. So for now, it's rest assured that the solo model itself can be taken to the data, even though there are a few, or more than a few actually, improvements that can be done to improve its fit to the real world. Okay. The next thing is calibration. Okay. So another way of viewing all of this is calibration. So let's think about it this way, right? Let's say that you had a production function like this, which is again Cobb-Douglas. Okay. H here, you can consider this as labor. And here is A times 8, L times L, A times H, which is basically in the textbook E times L, which is your effective units of labor here. Okay. The thing here is that the A is not measured, right? It's something that affects Y, but you cannot directly measure it. So one way of thinking about how big the A's are for the different countries is to use what's called a calibration method. So you're taking your production function seriously, okay? And then you're saying that in the US, your output is based on this equation here, wherein you have the capital stock for the US, the labor for the United States, and the hidden or unknown TFP value here for the United States, right? Now you can compare it to different countries, right? In particular, you can do this. You can isolate the TFP components here, and the TFP components will be functions of the ratio of the GDP of any country to the United States. Okay, capital of the United States to the capital of the JF country, the labor supply of the United States to the labor supply of other countries. You can bring this to the data and you can get a sense about how different the technology in country J is relative to the United States. Okay, so you're able to do this. You can set the United States TFP as 1. So everything will be relative to 1. And basically, this is what's happening, right? It's probably, well, what this is saying here, guys, is look at this is the 45-degree line, that red line here. This is predicted log GDP per worker, right? Predicted log GDP per worker. And what this is saying is that the TFP that's necessary to um, make the real data, this is real data, agree with the production function specification that we have here, will require basically that the TFP for other countries should be in fact much higher, right? Because the predicted log based on the fact that if the TFPs are the same, right? The TFPs are the same will be higher, right? So that's where the calibration matters. That um the predicted log GDP is in fact higher, right? Um, uh, under the assumption that there is no productivity difference between all of these countries and the United States. Okay, so to the extent that the real GDP is in fact lower, right, than the United States, that means that the technology for the different countries is in fact lower than the United States. You can see that here. Okay, so here's your predicted level of technology, and that in particular, as their GDP goes up, you will tend your predicted level of technology that will tend to match the real differences in GDP will become higher. So that's why this is a positive slope here, right? So this just tells you that a higher GDP per worker, right, is correlated with a higher predicted level of relative technology that will allow you to more precisely match the relative GDP per country. So this just tells us that differences in TFP are really driving a lot, right? of the variance of GDP per capita or GDP across different countries. That if you take a ratio between the United States and any given country, like here, okay, a lot of the difference here in GDP will come because of the difference in PFP here, right? Uh, and that's the situation. All right. So that's where growth accounting will basically end, right? I just wanted to end with that note that if you were to think about growth accounting, um, uh, where is growth coming from? The idea here is that a lot of the differences across countries is attributable to differences in PFP. Okay. And you can see that most clearly here in the calibration exercise that say Mankiw did. So these slides are well available online. You can like Google it. I will also make it available on Uvnet. But basically for the final, the most important component for your final is basically understanding these productivity differences through calibration using production functions here to estimate the predicted differences in GDP, or sorry, predicted differences in technology based on actual differences in GDP here and differences also in capital and labor. All right, so now let's return to the book. So that's a little tour on growth accounting, which really talks about this differences between factor accumulation and production efficiency. And the message here is production efficiency is a huge part of the story, talking about the differences in GDP per capita or GDP across countries. Differences in technology is a major component on how to explain these things. All right, so now we'll go to a lot more of the conceptual parts of the book, which are policies to promote growth. So I'm just going to let you read it, but I'm just going to point out some important ideas here. So some important ideas here is evaluating the rate of saving. We'll basically talk about, are we achieving the golden rule level of K? And the discussion here tells you that you can actually back out using the data similar to growth accounting. You can back out whether your K is less than or greater than um, the golden rule level of K. Okay? So I invite you to look at these numbers and these calculations, but these can be basically done. Okay, and it turns out that when calculations are done, the possibility of excessive saving and capital accumulation is intriguing, but appears not to be a problem. Okay. In practice, economists are more concerned with insufficient saving, which means the K star is below K gold. Next, changing the rate of saving. So this is one major way, according to the Solo model, to change the long run output per worker and the long run capital per worker, right? And some ideas here is that there is such a thing as public saving and private saving. Public saving is, of course, in the ambit or the power of the government to change, right? And you can change your how much the government can save and therefore invest due to this budget, to the appropriate and correct use of its budget. The other side of national saving is private saving. And a lot of what government is doing to influence the rate of saving is by incentivizing saving and incentivizing investment as well, which is the same similar concept. Next here is allocating savings, and it's important to allocate savings to investment with high returns. Okay, the government and even private businesses will invest in physical capital. Public capital is often called infrastructure, which is an important component of what the government can do. And another kind of capital that's important to invest in is human capital. Again, going back to the Mankiw Romer model, they are thinking of that human capital is an important part of capital, period, right? So it's not just physical capital, it's human capital that's important. And like we said earlier, if you include measures of investment in human capital, it improves the fit of the solo model, which means it's truly an important component that's part of the model. It really ought to be there. But capital um, should include not just physical capital, but human capital. Another concept here is that we should invest in particular forms of capital that have these positive externalities. If new and improved production processes are devised during the process of building capital, a phenomenon called learning by doing, such a byproduct of these ideas is called a technological externality or a knowledge spillover, right? So in the presence of such externalities, the social returns to capital exceed the private returns. So these are the kinds of investments that um, both the private sector and the public sector should be engaged in. Okay. This is, in general, it's going to be called industrial policy. So that's kind of important. So to identify capital or investments that have the highest returns, and that's going to be part of the job of the task of the government is to find these kinds of investments in order to improve long-run GDP per capita in the country. I won't spend too much time on this, but institutions are, remember we talked about proximate versus non-proximate. The long run or non-proximate are these institutional factors for economic growth, and that different institutions will allow countries to develop faster because it will allow more technology to develop um, based on the fact that certain institutions will allow private actors, uh, will give them the correct incentives to correctly invest their capital. Okay. So there's a huge literature here as well, but I'm not going to focus too much on that, other than the fact that institutions have been found as a possible long-run source for the differences in GDP per capita, or the long-run source of differences in TFP, total factor productivity. So encouraging technological progress. So we're gonna skip this. This is not super crucial to us because it's very time bound. So the next important part is 8-4, okay, which we will briefly discuss now, which are extensions to the solo growth model through endogenous growth theory. Okay. So what this is saying, guys, is in the solo model, technological growth is basically exogenous, meaning the growth in E or the growth in TFP is something that's given, that's going to happen, right? Where does technological growth come from? That is the question, right? And it's important to know because that's the source of long run growth. Right? So that's why they invented this endogenous growth theory. Now, this endogenous growth theory is built around the notion that the returns to capital should not be diminishing. Recall that in the solo model, the, the F as a function of K, small k, it's increasing, but it's increasing at a decreasing rate. So that there's a diminishing marginal product of capital. The basic idea for endogenous growth theory is simply that this delta K here, S of Y minus delta K, okay? That's just going to be equal to S of A minus delta. So note that this S times A is not S times F of K, right? It's not diminishing at all. So A is just some number and it's constant. Therefore, in the long run, this delta K over K, okay, is going to be greater than zero forever, right? Therefore, there is no steady state. There's no delta K, which is equal to zero. So this is the key for endogenous growth theory, that there is no longer this diminishing returns to capital. And this absence of diminishing returns to capital is the key difference between the endogenous growth model and the solo growth model. So this simple change in the production function can alter dramatically your predictions about economic growth. In the solo model, saving leads to growth temporarily, but diminishing returns eventually force the economy to approach a steady state. By contrast, in an endogenous growth model, saving and investment can lead to persistent growth in even in output per worker, even in output per effective worker. Okay. There are other complications, more involved versions of the endogenous growth theory, such as this two-sector model here. You don't have to really read through this because the details of which will not appear in the final. However, these ones will these sets of equations here will give you the same concept as the simpler endogenous growth model, in that there is no longer a diminishing return to capital, okay, which is the key difference. If capital and knowledge are the same, right, or both of them are capital, and the same way that physical capital and human capital are all both forms of capital, then there is no diminishing returns to capital. And therefore, even in the long run, you'll have positive growth in Y over EL, which is the idea. But what's good about the two-sector model is it'll tell you, hey, what are the sources for the fact that capital is not diminishing, right? That there's no diminishing returns to capital. And the source of that is that we are in fact investing in knowledge, right? And this investing in knowledge and in innovation will allow you to experience this endogenous growth, because this will allow basically it's the way for which capital will not face diminishing returns, right? If you do not invest in knowledge or in efficiency, then capital will basically be just a physical capital, and you will start to encounter diminishing returns to invest. So that's the key message for the endogenous growth model, really, that the constant returns to capital, no, not constant, non-diminishing returns to capital, that's important, the non-diminishing returns to capital, or increasing returns to scale in the production function, which means if capital and labor both increase, then Y will increase by much more than the percent in change. So if that's true, if capital alone is not diminishing, the reason that is because you're investing in knowledge. Okay? You're investing in ways to improve the use of capital. And that's the source of the endogenous. So ultimately, it's a super simple concept. Okay, so having said that, that's the end of chapter 8. All right, and I invite you to take a look at the problems and applications to help you practice for the final exam as well. On Thursday, we will go through chapter 8 very quickly after the presentations for macro news. But yeah, basically it's the growth chapter or topics on growth is basically going to be coming from chapter 7 and chapter 8, and a little bit from the Acemoglu slides that I just presented in this video. All right, I'll see you on Thursday. Bye-bye.